The first thing to fail is not the power plant. It's the schedule. A single train, loaded with 10,000 tons of coal, is late. Not by days, by hours. At the generating station, the stockpile gauge dips below the red line, the one that means less than 5 days of fuel on site. The control room makes a call. They begin to derate the unit. They throttle back the turbine, reducing output by 10%, then 20%. They are buying time, burning less fuel per minute. On the grid operator's screen, a chunk of capacity quietly turns from green to yellow. No alarm sounds in homes, but the margin for error across the entire region just vanished. The system is now balanced on a razor's edge of logistics, running on a buffer measured in hours, not days. This is the energy historian, uncovering the hidden systems that power civilization. And this is where a shortage of energy doesn't just mean less power. It means the intricate clockwork of modern industry begins to seize, one calibrated dependency at a time. We think of energy shortages as lights flickering or gas lines. That's the end stage. The real collapse happens upstream, in the industries that convert raw energy into everything else. They are the transmission gears between the primary source and your daily life. When the energy flow slows, these gears are the first to grind. They don't just slow down. Their fundamental economics invert. Their physical processes break. They stop. And when they stop, the chain of production snaps in places most people never see. There are 5 critical industries that act as these fracture points. Not random victim-specific, high-leverage systems whose failure cascades with terrifying speed. This isn't about saving electricity. It's about the structures that depend on massive, continuous, predictable flows of power and fuel to even exist. First, bulk chemical manufacturing. This is the invisible foundation. We're not talking about boutique labs. We're talking about the colossal, continuous flow plants that make ammonia for fertilizer, ethylene for plastics, chlorine for water treatment, and sulfuric acid for, well, everything. These are thermodynamically brutal processes. A modern ammonia plant, using the Haber-Bosch process, runs at around 450 degrees Celsius and 200 atmospheres of pressure. It doesn't just use natural gas as a fuel. It cracks it apart to get the hydrogen to fix nitrogen from the air. The molecule itself is built from fossil fuels. These plants are designed to run flat out, 24/7, for years. They are capital-intensive monsters, where downtime is measured in millions of dollars per day in lost revenue. An energy shortage doesn't just make it expensive to run these plants. It makes it physically impossible to run them safely. You cannot turn down a catalytic cracker or a steam methane reformer like a dimmer switch. These are equilibrium systems. Reducing feed or energy input risks a temperature drop that can cause the reaction to stall, or worse, lead to catalyst poisoning or dangerous pressure imbalances. The only safe response to a severe gas curtailment or power interruption is to initiate an emergency shutdown. A full shutdown and restart of a world-scale ethylene plant is not a matter of days. It's a weeks-long, meticulously sequenced procedure. Every day offline means thousands of tons of product not made. The entire global supply chain for polymers, fertilizers, and industrial chemicals is built on the assumption that these plants are always on. If they trip offline across a region, the deficit isn't filled next week. It lingers for months. The first domino isn't the price of plastic. It's the absence of the chemical building blocks themselves. Second, primary metals production. Aluminum is called congealed electricity for a reason. Smelting alumina into aluminum is an electrolytic process of almost absurd energy intensity. It takes about 15 megawatt-hours of electricity to produce 1 ton of aluminum. That's enough to power the average American home for well over a year. An aluminum smelter is not a factory. It's a dedicated power plant with a metal-making attachment. The pots, the electrolytic cells, run at about 950 degrees Celsius. The molten aluminum sits at the bottom, a shimmering silver lake. Once started, these pots must be kept at temperature and current continuously. If power is cut for more than a few hours, the electrolyte solidifies. The pot is frozen. A frozen pot is a total loss. It must be physically demolished and rebuilt at a cost of hundreds of thousands of dollars per pot. A smelter has hundreds of them. So when an energy shortage hits, the smelter manager faces a horrific choice. They can try to ride out a price spike, hemorrhaging money with every megawatt hour they buy at spot prices 10 times the norm. Or they can execute a controlled power down, a slow, costly process of idling pots. During the 2021-2022 European energy crisis, that's exactly what happened. Over half of the EU's primary aluminum capacity went offline. It didn't come back when prices eased. Restarting a pot line is a slow, capital-intensive gamble. You're betting energy prices will stay low for the years it takes to recoup the restart costs. The metal doesn't just vanish from the market. The capacity itself vanishes from the map. The supply chain for everything from cars to cans to construction materials loses a foundational layer. And it doesn't return quickly. The industrial base itself contracts. Third, industrial gases. This is the most stealthy, critical collapse. The air you're breathing is mostly nitrogen, but the nitrogen used in industry to purge pipelines, to create inert atmospheres in food packaging, to cool superconducting magnets in MRI machines, is produced by cryogenic air separation units. These are massive, energy-hungry refrigerators that cool air to 200 degrees Celsius, liquefying it, and then distilling it into its components: nitrogen, oxygen, argon. They are enormous electricity hogs. A single large ASU can draw 50 to 100 megawatts, the output of a small power plant, and it runs all the time. The product is often piped directly to nearby customers, like steel mills or chemical plants, in a network known as a pipeline alley. Here's the catch. You cannot store industrial gases at scale. Yes, there are some liquid tanks, but the primary mode of supply is just in time, straight from the ASU through a pipeline. If the ASU loses power, the pipeline pressure drops within minutes. For a steel mill using nitrogen to prevent explosions, or a semiconductor fab using ultra-pure nitrogen to blanket its production lines, this is an immediate emergency. Their processes must stop. The entire modern manufacturing ecosystem assumes the continuous, invisible flow of these gases. An energy shortage doesn't just raise the price of oxygen. It threatens to stop the flow entirely, forcing hospitals to ration medical oxygen and microchip plants to halt billion-dollar production lines. It's a leverage point almost nobody sees until the pressure drops. Fourth, integrated logistics and freight. This is where the shortage becomes physical movement. Modern logistics is a just-in-time ballet, powered entirely by diesel and electricity. The container ship runs on heavy fuel oil, but the cranes that unload it at the port run on grid power. The diesel truck takes it to the rail yard, where the electric locomotive, or the diesel-electric one, picks it up. The warehouse it's stored in is lit, cooled, and operated by electricity. A shortage doesn't have to mean no fuel. It can mean a price spike that makes moving low-margin goods economically impossible. Or it can mean rolling blackouts that shut down port operations for 8 hours at a time. Consider a port like Los Angeles or Rotterdam. Cranes sit idle. Trucks queue for hours because their refrigerated units can't risk turning off. The containers stack up. The delay compounds. A 2-day delay on a ship becomes a 4-day delay at the terminal, becomes a week-long shortage on a store shelf. But the deeper collapse is in the logistics math itself. Freight moves on razor-thin margins. A 30% increase in the price of diesel can erase the profit on an entire cross-country haul. When that happens, carriers park trucks. They refuse low-paying loads. The physical movement of goods becomes selective, prioritizing only the most essential, high-value cargo. The system doesn't break. It selectively abandons whole sections of the economy. The stuff that keeps daily life normal, the replacement parts, the non-urgent retail goods, the materials for small businesses stops moving. The map of commerce shrinks. Now, the fifth and final collapse point is the inversion. It's not an industry that consumes energy. It's the industry that manages energy's absence, data centers, and digital infrastructure. This seems counterintuitive. The digital world is weightless, right? It runs on silicon and ideas. But the cloud is a physical place, a warehouse full of servers consuming vast amounts of electricity, not for computation, but for rejection. Over 40% of a data center's power load goes to cooling, to removing the waste heat the servers produce. These facilities are built with dual power feeds, massive backup generators, and banks of batteries for the milliseconds it takes those generators to spin up. They are designed for resilience. But their resilience is predicated on being the highest priority customer on the grid. They pay a premium for that reliability. In a prolonged, widespread energy shortage, that social contract phrase. When the grid operator is facing cascading blackouts, the political pressure to keep hospitals and homes powered will overwhelm commercial contracts. The data center may have its own fuel, but what about the water treatment plant that supplies its cooling towers? What about the natural gas compressor stations that deliver fuel to its generators? Its island of resilience is surrounded by a sea of failing infrastructure. The digital economy assumes constant, perfect uptime. A prolonged brownout, or a directive to drastically curtail power, would force an unthinkable triage. Which data gets to live on powered servers, and which gets throttled or shut down? The collapse here isn't of hardware, but of the continuity assumption that underpins global finance, communication, and logistics tracking. The nervous system of civilization goes dark, not for lack of data, but for lack of joules to process it. The mechanism that ties these 5 collapses together is time. Not clock time, but process time. Each of these industries operates on a different, inflexible temporal scale. The chemical plant runs on reaction time, the physics of catalysis and equilibrium. The smelter runs on thermal time, the slow bleed of heat from a molten mass. The air separation unit runs on pipeline time, the immediate pressure of a flowing gas. The logistics network runs on schedule time, the synchronized arrival and departure of thousands of moving parts. The data center runs on uptime, a binary condition of 1 or 0. An energy shortage imposes a new, dominant time, the depletion rate of the stored energy buffer. When the buffer time becomes shorter than the process time, the system must break. It has no other outcome. This is why strategic fuel reserves, while politically comforting, are almost irrelevant to industrial collapse. You can have 1 billion barrels of oil in a salt cavern, but if you lack the continuous electrical power to run an aluminum smelter's potline, or the steady gas pressure to feed a steam methane reformer, the reserve doesn't matter. The industry still stops. The resilience isn't in the stockpile. It's in the flow. The entire modern world is built not on stocks of energy, but on its instantaneous, reliable flux. We didn't build a civilization that uses energy. We built a civilization that uses energy. We built a civilization that is energy, temporarily crystallized into structure and order. When the flow falters, the crystallization process reverses. The structure begins to dissolve back into chaos, one dependent industry at a time, following a predictable sequence of breaking points. The hidden infrastructure is always there.